right? And then let's go to the whiteboard. And we are all set, right? So let's get started. So you guys can help me out. And these should be fun problems, okay? So you're gonna do scans, right? 3D scans, was it? 3D scans. What's a 3D scan? All right, and then we want to detect cancer, right? So, all right, so remember, how do you approach this? Usually inputs and outputs, right? That's basically what you want to do. So circle indicates model. What is the model? You know, whatever we need it to be. And then we've got inputs and outputs. And then after that, we're going to want to define what X and Y are. All right, so, you know, this is so I don't forget cancer detection. Do you think that this is possible to do? Yeah, right. This is actually something that's been showing evidence that it could work, that it's helpful, right? So so let's think about all these problems, right? Answer. All right, so how do we start? Where do we start? What's easy? So start with the easy things to define. Yeah.
Define X and Y.
Right, but it's okay. So what?
So I guess X could be the data from 3D scan.
Well, yeah, very good. X should be the data.
And Y can be whether it's successfully is cancer or not.
Very good. All right. So the output is then what? This is a classification problem.
Yeah, it's not just going to be a yes or no.
It's not?
No.
What's it going to be then?
You could have lung cancer, you could have heart cancer.
Well, I mean, in machine learning, you want to simplify things. So you're going to build a model not for all types of cancer.
One, right.
Yes.
Okay.
That it's so although, you know, nowadays you do want like this super AGI, right? An AGI means artificial general intelligence. And the definition is that it can do multiple tasks effectively. So, but an AGI, it's very, you know, complicated to do. So we don't want to start that way.
Right.
That's a goal, but then you're talking about, you know, almost, you know, artificial intelligence that's, you know, very, very smart. So let's start simple. So some type of cancer, you know, brain cancer, okay. 3D scan, right? So we can say maybe brain cancer, tumor, etc. So then we just need a model that highlights, right? That highlights yes or no, right? So how many classes do we have then for this problem? 2 classes, right? 0 or 1 possibly, right? Okay, so we can start defining our X matrix and our Y vector. See, it starts to take shape. Okay. Oops. All right, so then we have here, how many columns in Y? This is Y. 1, right? What are the values? 0 or 1, it could be -1 and +1, as long as you have 2. So let's say 0 and 1, right? Something like that. Okay, very good. So now we need to define what is a sample, right? So that's an important one. We need to define these kinds of things. So where do you want to start? We should probably start with what is a sample, okay? So in this case, we want to define what is a sample. So what's a sample? A 3D scan, exactly. And what is a 3D scan? What do you think a 3D scan would be? Huh? Yeah, exactly. It's like an image that's 3-dimensional, right? So they, you know, maybe they obviously it's not a camera. It's a CT scanner or whatever that is called, right? So they have a CT scanner. I think it's called like that. I'm sure it's an acronym for something. But this device gives you images, but they're basically 3-dimensional. So that means there's like a whole bunch of layers in there, right? So, you know, all of those. They're images. Yeah, pictures. Yeah, somebody said, I think pictures. Okay. Do you guys agree? Okay. So then what do? What else? What's the easiest? And please take the easiest approach, I would say. So remember, we need to, what did we say this letter was? N or M? N. And then this letter was M. All right, so we want to define those, right? So which one do we start with? N? Okay, so what is N? Remember, you need to make a logical, yeah. What is N? Number of samples, very good. Number of 3D scans. So how many do you have?
Can we say 50, or is that too little?
It may be too little.
I wouldn't know, I don't know much about that.
No, I know. This is where you would work with a doctor, right? Go to a hospital, but you can make some reasonable, you already define a few things like doctor, hospital. So then how many of these can you get, do you think, reasonably speaking? Remember, they're very specific to a type of cancer. Huh? 1,000, right? So you're basically saying, you know, with some certainty, I can't get 1,000,000 of these, but I can get 1,000. Okay, so that sounds about right to me. Okay, now it is a 2-class problem, so that's a good thing. All right, now we need to define M. Now M are the columns, right? And those are called the features. Okay, very good. So how many features will you have here? What do you think? How do you arrive at that value? Yeah.
What makes up the actual scan?
What makes up the actual scan, right?
Maybe coordinates in the picture deciding what different things are, maybe a curvature in this brain looks like a tumor, maybe it's malignant and not a problem.
Right. Right, and so you're basically saying, do you create a set of features that look at curves and then give you values, and that's feature engineering? Or do you take an even simpler approach where you just give it the raw data, the image, and let the machine learning algorithm figure it out? Give it the images, right? That's the simplest. Now, there's a lot of ways of solving this nowadays, for instance, using pre-trained models. So when we look at, if you guys take ITS 530, you will see that, right? You will see how you would actually want to use a pre-trained model to give you features. But for now, let's just use the data itself, right? So all the raw data. So let's, for the sake of argument, let's say that these are going to be, basically not that big. So what's a number here that wouldn't be that big? Let's just, to make things simple, 30 by 30 by 30. Obviously here, this strongly depends on a CT scanner. So you have to go in, whatever that machine is, whoever makes it, and that machine is going to produce these images. And then what you can do, if they're too big, I want to say they're probably big, that you would downsample, right? So there's a lot of techniques in the image processing toolkits. We'll use some of them to play with images and downsample them and so on. Does that make sense? But let's say for the sake of argument that it's 30 by 30 by 30, right? So we want to use that raw data. So each sample is a cube of 30 by 30 by 30. Does that make sense? What is that? 30 by 30 by 30. How much? 27,000. Wow, that's pretty big. Okay, so you've determined that. Then how many features do you have? How many? 27,000, right? So if you're going to use all of it, you have 27,000. Now here, my recommendation would be, as you start to do this analysis, downsample these even further, okay? Just so that your algorithm, you can get it to run, and then you can always go back to making them bigger. Remember, you should always write your code so that it's pretty easy to downsample or oversample, to increase the size, get the size back to what it is, or scale it down, okay? So always make your code like that. But does this make sense? So yeah, so this one's pretty straightforward, actually. Whenever we get these image ones, you can see why people have done so much research in image-based machine learning, right? Because they're very straightforward usually to do these kinds of analysis. All right, so we've defined, so we have basically 1,000 samples, and the vectors here at each row is of size 27,000. Now the values in here will be what? Like pixel values, let's say, right? From 0 to 255. Okay, and then for each one, you've got these labels. Does that make sense? Have we answered all the questions? Are we missing something? No, no, right? I think we've got everything. Now, one important one, here's an additional thing where this might present a challenge. So you have a CT scanner, right? And you're using it over a year, let's say. Over that year, you've collected 1,000 scans. So that's, probably 1,000 patients. Now, will all of these scans have, will they be scans that have cancer or scans that don't have cancer? What do you think that distribution will be? Not all of them will, right? How about so will the majority be the ones that have cancer or ones that don't have
I
cancer?
think majority
Don't have cancer, right? So what do you think that ratio would be?
maybe 60-40.
60-40, okay. I think it's probably even less than that. Hopefully, right?
That would be better, yeah.
Yeah, hopefully it's let's say it's actually 90 to 10%, right? And that might be even so. What do you think about that? So that means 90% is class 0, right? Let's say that's not cancer, and 10% is class 1, right? So that means 900 examples are no cancer, and then 100 examples are cancer, right? So you think that might present challenges to a machine learning algorithm?
Maybe you'll get
Biased, right? Yeah, exactly. Very good. So machine learning is all about differences. Okay, very important. Now, whenever you have a majority class like this is called an imbalanced data set. As you will see with a lot of the examples we're going to do, because they're very for educational purposes, they're always very balanced. You always want balance in machine learning. But in the real world, you don't get this, right? In a bank, you don't get fraud that much, right? You do get fraud, but a lot of the transactions are not fraud. Here, hopefully a lot of the cases would be of no cancer, right? So it becomes a little bit of an issue. You have a little bit of an issue. So what should you do? Probably stay with the data as is. Another thing you can do is keep the 10% of the cases that are cancer and then drop a lot of the cases that are not, like from 90% to 20%. That balances it a little bit, but it's no longer representative of the world. And then this will lead us into a lot of the performance metrics that we're going to study soon, which basically say, well, what do you want? Do you want to miss cases of cancer, or do you want to just detect everything and then have a second test that rules out things? You know what I mean? So that's going to be something called precision and recall, which we will study a little bit later. Okay, does that make sense? Those are very important things. So that's what's really nice about machine learning, is that you have in general ways of measuring the performance of your models. Got it? Does this make sense, guys? Any questions about this work problem? It's an easy one, right? Because we're dealing with images, and so it makes it pretty easy and straightforward to do. All right. So I'm gonna do probably one more example. So let's think about this one. Gonna